In this video, we shall discuss the solution of a numerical problem on finding current in a cylindrical conductor. If you observe the problem carefully, it's given here cylindrical conductor. So the conductors carry current and it is a cylindrical wire. This is the cylindrical conductor. Radius 2 millimeters given. The radius is the distance measured from the axis to the surface of the conductor. 2 millimeters. The current density J varies with respect to distance from the axis. That means the current density J varies in this direction. It is given here J 10Q e power minus 400 R. So the current density, which starts from the axis, decreases exponentially towards the surface of the cylinder. The direction of the current density is A cap Z. That means current flows in Z direction. But the value of the density varies with respect to radial distance. So this information is given. Here R is taken as the radius. Now we shall find the current I from J using this relation. I is equal to surface integral of J. I is equal to surface integral of J. Value we shall substitute 10 cube e power minus 400 R A cap Z. Now the distance ds. The differential surface is always defined by two differential lengths. If you observe the problem carefully, you can easily guess the differential surface element should be R dr d phi A cap Z. How we have written this one? If you want to know more about this one, we can also go in this way. In cylindrical coordinate system, three variables are there: R, phi, Z. When R changes, it gives us the differential length dr. When angle phi changes, it gives the differential length R d phi. And when the Z changes, it gives differential length dz. So to define a differential surface element ds, we have to multiply any two differential lengths. So in this problem, the current density J is a function of R. It varies from 0 to 2 millimeter. In the problem, it is mentioned that J varies from axis to the cylindrical surface of radius 2 millimeter. So R varies. So we have to integrate with respect to R. Obviously, phi varies because current flows throughout the conductor in all the direction, 2 phi. But J does not vary with respect to Z. Density doesn't vary. Current flows along the wire, but density doesn't vary along the wire. Density vary across the wire. Maximum current density at the center, and which decreases towards the surface. So by multiplying these two, we can have R dr d phi. The direction of the this surface is upward. So now we can get the output of dot product 10 cube e power minus 400r az dot az is 1. So into r dr d phi. So the variables are r and phi. 10 cube is constant. All r terms put together. Phi component is also to be integrated. Limits are clear. For angle complete cylindrical conductor, the angle should vary from 0 to 2 pi. For r, the radius should vary from 0 to 2 millimeter. So 10 cube. Let us integrate the phi term first. It's easy. Integration of d phi is phi. Upper limit 2 pi minus 0 is 2 pi. Now we have to integrate with respect to r. This can be integrated using any appropriate mathematical method if you have. Okay, so we can use the product rule for the integration of r and e power minus 400r. But I'm going to use Bernoulli's method, by which you can directly get this answer for this integral, according to which the non-exponential term, that is r, should be kept same without any change, and the exponential term, the decaying exponential term, should be integrated, divided by minus 400r. So in Bernoulli's method, the integration is easily done for the two terms involved. Among one is exponential. So the non-exponential, retain it as it is in the beginning, very first step. Exponential, you integrate it. Next, we shall change the polarity now, minus. So for every step, the sign should be changed. Next, hereafter completely, this r term should be kept on differentiating. Exponential term should be kept on integrating. So differentiation of r is 1 here. Integration of this exponential term is e power minus 400r divided by minus 400, which is already there. So one more minus 400 comes into picture. So in the next step, the sign has to be changed from minus to plus. Now this 1 has to be differentiated, which goes to 0. And this exponential term has to be integrated, but 0 into anything is 0. That's why we stop here. The limits are 0 to 2 millimeter. 2 milli means 0.002. So this completes the integration of r into e power minus 400r. So in the next step, we have to apply the limits to r. This has to be handled carefully. This is 2 pi into 10 power minus 3. Take a flower bracket. Let us go with the first term, upper limit 0.002 into exponential of 400 into 0.002 divided by minus 400. This is the first term with upper limit minus, we shall put the lower limit. Lower limit is 0, so the complete term goes to 0. Now let us move to the second term minus. First apply the upper limit, that is a power minus 400 in place of our 0.002 divided by minus into minus plus. It's going to be 400 into 400. This is about the upper limit minus the lower limit being 0. If you put r value 0, e power 0 is 1 divided by again 400 into 400. So that completes the second term. Third term is 0. So that ends the substitution of the limits. Next is simplification. So here we can use calculator and work out this value. This complete term gives us 2.25 into 10 power minus 6. Similarly, we shall work out this. That will be 2.81 into 10 power minus 6. So minus into minus plus the last one. 6.25 into 10 power minus 6. Minus 3. So this is plus. Yeah. 10 power minus 6 can be taken out as common factor. Then you will be left with 2.25. This is minus here because of this minus 400. Then minus 2.81 plus 6.25. So finally, we get the current as somewhere around 7.4, 8 milliamps. This is the total current flowing through the cylindrical conductor in that direction.